Hello again. This video is set up to give you some examples of some different types of problems you might encounter when you study friction. Now, we're not going to do just simple basic plug and chug questions. You should be able to manage those on your own. But here's some questions where you can get a chance to think about how to take them apart, find the constraints, deal with the technical definitions, and obtain the correct answer. So hopefully you'll enjoy these 4 examples. So let's revisit this ramp question I showed you a little while ago. Now that we have friction in our back pocket, so we could put a mass on a ramp, and we have friction, we have gravity, and we could say, okay, well, one of the questions you could be asked is, what is the minimum value of theta upon which this mass would begin to slide? Okay? Clearly, if it's almost vertical, it's going to fall. If it's flat, it's not going to move. So there's somewhere in between where this mass will begin to slide. And the question we want to ask ourselves also is, what will it depend on? In this particular situation, we're going to look at our fundamental constraint here. What is the thing that's going to cause this thing to slide? And what you're going to say here is that the net force on ramp will be not equal to 0 and less than 0. Okay? Now, one of the things we have to remember is the force of friction when it is static it doesn't provide the static force at all times, okay? It will provide, let me rephrase this another way, instead of providing, it will match your applied force until exceeded. And then you get motion. So if we want this object to move initially, okay, some relative angle, this is not moving. The frictional force is matching the force that is generated along the ramp by gravity. Not anymore, because if it was actually at its total amount, then the object would be moving up the hill, which would be pretty remarkable. So it's kind of like a spring. It responds. However, there's a point where the frictional force, the static force, will be exceeded. And when that happens, then we have motion. So this situation, our fundamental constraint here, the net force on the ramp will be equal to 0 and then less than 0. We'll assume that's negative. Okay? So this is a concept we need to really understand. So we have our fundamental constraint, but this is part of a technical definition. Do we really understand what the static force means? So what we're going to say here is so for F net equal to 0, we have Fr plus F friction equals 0. Okay? Now this is a balance point. So now we're going to choose the maximum frictional force. Okay? That's the most it can produce. And that'll give us our theta. So here we have, from the example of the extremes before, we're going to have F sub g sine theta plus, now we have to be careful here about our angles and our directions, because this is going to give us positive numbers. So what we're going to do in this case is we're going to make it negative. F sub g mu s cosine theta equals 0. Okay, so we can get rid of some things now. We can certainly get rid of the force of gravity. We don't care. And then we can say that mu sub s is equal to sine theta over cos theta, which is tan theta. So remarkably, the coefficient of friction, that is the theta, so to speak, for a given coefficient of friction that will cause us to begin to move is simply equal to the tangent. That's a pretty amazing just little relationship. And a lot of times this is the kind of thing that a young student of the material needs to stare at a little bit. But again, if you use my suggestion that this motion is really just one-dimensional, don't make it more complicated, then your equations immediately become comparatively easy. Another question I've used in the past that's kind of interesting and it gives you a sense of understanding is if we have this mass sitting on a tabletop with a known coefficient of friction, a known mass, in this case 60 kilograms, we have a 10 kilogram mass here and a known coefficient of friction 0.3. If I put a force against this mass so that it will be held against the side and not fall, the question is, what is that force? And if I were to apply that force, would this entire assembly begin to move or will it stay put? So the constraint here on the first part is that this force here, okay, is the weight. So we're going to have to say the gravity force would then have to be equal to the frictional force. Okay? And that's equal to mu times the applied force. Okay? We don't have mg here, and this is what you have to be careful of. You have to understand this force here is the one that's pressing these two surfaces together. Gravity in this case is actually pulling it along. So let's expand this and have a look. Then we have mg equals mu Fa. Fa then is going to be equal to mg over mu, which is equal to, in this case, m1 already. Maybe we should point that out. Okay, so now we have 10 times 9.8 divided by 0.3. So we take 98 divided by 0.3, and we're going to get 326.6. We'll say 327 newtons for simplicity here. Okay? That's our applied force. So that's the first question. Very straightforward. But the trick, if you will, to this, or the important concept, is that you understand that the normal force is not necessarily gravity. It can be something else. Like when you lean against the wall and your hand is pushing against the wall, the pressure between your hand and the wall is in part due to you leaning, but isn't really all that much to do with gravity, a little bit. But so you have to be careful about these things, and we'll get back to these. So let's look at the second part now, and let's see if this whole assembly will actually move, given that we're applying 327 newtons in this horizontal direction. So let's just keep things going here. So we need to find out the force of friction, okay? And this is going to be equal to, now we have the normal force on this surface. It is going to be the weight. But here's the other point. We have to think of this mass and this mass, because this mass is kind of attached to this now, and its weight is being supported by this one. So now we're going to have a situation where we're going to have mu, this will be mu 2s, but we'll just say mu 2 for now, times m1 plus m2 times g. This is going to be equal to 0.2 times 70 times 9.8. And we'll have a quick look at what that is. Wish I could do these things in my head like I used to be able to. But inevitably, when I'm doing a video, I'll make a mistake. So 137.2, we'll say 137 for simple math. And notice that the force of friction is less than the applied force. This will give us motion. Now, then we have the next step to this. We're asked to calculate the acceleration. So we have to be careful here because we have to do two things. We have to remember to change to the coefficient of friction, 0.15. And we have to remember when we accelerate, we're accelerating this mass and this mass. So when we first determined if this thing was going to move, we got 137 newtons worth of frictional force. But now we have to recompute this. We can cheat a little bit here, but I'll show you the proper way to do it first. We have mu sub k, and then we have m1 plus m2 times g, and you get 0.15, 70, and 9.8. And we'll say that's roughly 108 newtons. However, in this question you can, of course, do it quicker because you notice that m1 plus m2 and g are constant in both equations. The only difference is the coefficients of friction. And so you can have F friction due to kinetic over F friction static is simply equal to 0.15 divided by 0.2, and when you're finished you have your frictional coefficient here, or friction is 0.75 times the static one. So if you see this, it allows you to make a shorter calculation. Okay, well let's go back and see what the acceleration is going to be here. So we had our net force then is equal to 326, or 327 say, minus 108 due to friction. Okay, so this gives us 219 newtons. And then acceleration is equal to the force divided by the mass. And so we would have 219 divided by 70. You have to add both masses, okay? And then just do simple division here. And I get 3.13 meters per second squared. So there are three issues with this particular question. Remember, people, as I've said to you many times, you will not solve these problems by memorization. You're going to have to think your way through them. Now, I know this year we're not testing the same, but that will come. The issue here is to look at the fundamental constraint. The fundamental constraint in this particular problem was simply this, that this force holds this mass against this one. Everything else falls out of that. That's all you have. So then what is the technical definition of that? Well, and we have to find out what the frictional force would be here necessary to oppose the weight. Okay, and when we get that, then we say, okay, well then what is the consequence of the entire system? And all that is just one technical definition after another. And again, we come into situations where, well, will it move? Well, we have to calculate the amount of frictional force. We found it to be 137 newtons. Then we say, okay, yes, it will move because we have 327 available. But now we have to turn around and go back again. and recompute our frictional force based on this lower coefficient of friction, because now we're moving. And that gives us a frictional force of only 108, and then a net force of 219, and then the division here. But again, you have to remember both masses. So none of this in any real aspect is all that difficult. But to put it all together and to think it through is the task before you. That is what we do in this science. That is what we do going ahead. If you are ultimately going to be an engineer someday, design an airplane, or design some other technical thing, you're dealing with something that is 1,000 or hundreds of thousands of times more complicated. And you have to reason your way through everything, because whatever you're building, designing, or whatever has probably never been done before, or never been done that way before, or has different constraints on it than the other ones had. You can certainly learn from what's gone before, but you're still going to have to think your way through, find out what the constraints are, take your technical definitions. So this is a bit more involved question that you might get with ramps. So what we have here is we have two masses. We have the mass on the slope. We have a mass hanging over the edge of a pulley. We have a coefficient of friction, both static and kinetic. And we have an angle. So the question could be asked a lot of ways, and we can play around with this quite a bit. We could say, for example, what value of theta would keep this from moving? Would be the point where it starts to move. We could say, given theta and so on, what value of the coefficient of friction would cause this thing to begin to move? Which way will it move? Okay, and all the rest. And you might say, well, gee, it's pretty obvious. And it really isn't, because if you think about it, if we had a pulley just like this, and we had our M2 and we had M1, like so, this being 10 and this being 7, it's going to go this way pretty aggressively. And this is another example of Van Bemmel's law of extremes. If you had a table that's flat, and you had M2 here and M here, like so, and mu would be 0, then the thing's going to go this way. And the lighter one would win. So the answer as to which way it will go is therefore by no means instantly known. And we have to figure it out. So we're going to start this problem by first looking at the fundamental constraints and how we can figure out what our acceleration is going to be. One of the things that we want to look at is recognize that we can compute A and either way. So this is we're going to say this direction is negative and this direction is positive. Remember that in my first explanation, this is linear motion. Although we have a ramp and a corner, in the end, this business can only go this way or it can go this way. It can't go somewhere else. So let's not turn it into a problem that's more complicated than that. So the way you've been taught so far to compute what is happening is we're going to calculate the components of the three forces involved. And we're going to be careful about how we calculate them to make sure that the directions are appropriate with what we understand. I'll give you an example before we get into it. We know that M1 is angling down. It's angling this way down the slope. It will be acting this way. So we want to make sure that it's indicated as a negative in this example. The mass 2 that's pulling down here, of course, but it's pulling up the slope, we want to make sure that this force, this weight here, is one that is taken as positive. Now, what is interesting, of course, is the friction, because the frictional force is going to oppose. Now, let's think about what it's going to oppose here. It isn't moving, so the typical choice of the friction opposing velocity doesn't work here. But what the frictional will do, especially in the case of the static friction, is it's going to oppose the unbalanced force. So what we're first going to find out here is, does this force pulling down the ramp, is it greater or less than the force pulling over the top? Because although we can calculate the force of friction, we don't know what direction it's going. And that's the tricky part. So we need to do a preliminary calculation to see whether it's going to go this way or this way. When we know that, then we can compute the friction and add it correctly to our equation. So let's do that first. So we're going to take the components first of M1. And remember what we said before is that we want to know whether this is sine or cos. And once again, we know that if this is a flat table, and the mass is sitting on the flat table, that this is going to be 0. So we know it's sine. So therefore we're going to say the force on the ramp of the first mass is equal to negative. And we have to be careful here because we want to see if we want to use G as negative or positive, it gets complicated. So we're going to take it as positive in this case, because not because we're cutting corners, but because we're setting up our own set of directions. And the 9.8 doesn't necessarily tell us that directly. So we're going to say negative 9.8 times the 10 kilograms times the sine of 35 degrees. Okay? And then we'll do these two and then we'll compute the answer. So FR2, this one's going to be positive because it is pulling up the slope. This is going to be 9.8 times 7. And there's no sine or cos because this is a full free weight, so there's no extra calculation. So I went ahead and did the calculations. So if you see here, negative 9.8 times 10 times sine 35 gives us negative 56.2 newtons. Going up the ramp is plus 68.6 newtons. The net force is the sum of these two. Because the one is negative, we end up with 12.4 newtons. Now that means then that the net force is pointing up the ramp. Now we're not done yet. Not by a long shot, because we still have to calculate the force of friction here. And the question will be is, does this move at all? Okay, and if it does move, then we're going to have to calculate the acceleration. So that's the next step. So we have a net force that we calculated based on the gravity effects pulling down the ramp, the gravity effects pulling this mass this way. We'll call that Fnet1. And we want to calculate Fnet2 now. And we want to then add in the effects of friction. So let's have a look here. We're going to have 12.4 minus, then we're going to have mu, and then we're going to have, in this particular case, m1g, taken positive. Now, we know it's cosine because if theta was 0, this would be lying on the table and we would have a maximum. So we're going to say cos of 35. And so let's expand this once again and then we'll do a calculation. 12.4 minus quantity 0.3, it's the static case, nothing's moving yet, times 10 times 9.8. Okay, there's no negative because this has got nothing to do with its motion, this is to do with the normal force, times the cosine of 35 degrees. So now we look at the definition of the force of friction, which is mu times the mass, m1, not m2, and g and cos 35. We calculate all that, we get 24.1. Now we had a net force of 12.4 left over from before. The force of static friction is 24.1. And what this means is that no motion can occur unless this force is exceeded. 12.4 is less than 24.1. So therefore, the second net force will be 0. This force here does not respond at 24.1. It will answer back only with what's pushed against. So if you have, this is where we have to be careful with the idea of the static friction forces, because it does not push against you at its maximum. It will push against you and match your exact force until it can no longer do so. And so, in this case, this is actually going to be negative 12.4. Okay? which leads to this. So it's a very interesting question because you have lots of things happening, but in the end, nothing's happening. But it shows you how we have to calculate. And notice that, especially in this particular case, this is a two-step process because we don't know which way friction is going. So you cannot determine whether this is a plus or a minus until you first determine which way the balance of the forces is traveling, is forcing us. Now, before we leave this topic, let's look at an application that applies to many of us. If we end up on a slippery surface, be it ice or something else, we always walk with our feet very close together. And the question is why is it so easy for us to fall? And why are these falls so sudden? Now we know, first off, that the coefficient of friction here is effectively 0. Not quite, but pretty close. And we're going to give that to us. So that's not enough of a reason. Let's look at what else is happening. So I'm going to draw in some things here to figure out what we're doing. So we have a 1 foot that's going to be extended here. And so we have there's a normal force. Okay. And we also have a horizontal force. Okay, horizontal force. So if we have friction on our feet, if we're standing perfectly vertical, the horizontal force is effectively 0. So at vertical, the horizontal force is basically 0. Now we can have a value of theta here, okay? Well, maybe I shouldn't put it there. Well, we maybe could have a theta like this. Well, maybe I shouldn't draw it like that either. Let's see if we can fix this. So we have a theta. We all know where it's supposed to be. And so as theta increases, okay, the horizontal force will increase and the normal force will go down. So the horizontal force is equal to, we can say, let's say that the weight is half, so we could say 1/2 of the weight of the person times the cosine. So when theta is basically 0, right? Okay, so there's cosine of theta. And the horizontal force is going to be equal to, we'll say the same 1/2 because it doesn't really matter, sine theta. So if we look at our graph over here, we have our cosine function doing this, and we have a sine function doing this. And so what happens as the angle increases, as the theta becomes larger, the values drop. This stays about the same, but this increases a lot. So as you move your foot away a little bit, this changes slower and this changes very quickly. And so what you end up with then is not only a reduction in friction, we get a reduction in friction in the frictional force, but we get an increase in the force acting against us. And so that's why falls are very sudden, because you've got both things going against you. You're losing your capability of maintaining your position, and at the same time the force that's working against you to do that is increasing. So when the mu value is so low as it is, even your foot may be more than an extra 5 or 10 centimeters is all it takes, or a slightly greater amount of force because you've shifted your balance from one foot to the other, and down you go. And it's very sudden, so you can't prepare for it. Okay, so here's an example just of how friction works day to day. And I like to make sure we think about how these things are acting in our daily lives and not just some theoretical questions out of textbooks. So there you have 4 examples, 4 different ones, fairly different ones. Some of them that, as you can see with the first one with the pulley and not getting an acceleration can happen, and knowing your way around it. And this is, of course, testing your understanding of concepts like static friction force and recognizing that it isn't always at its maximum. It's actually what you give it up to the maximum. And some of the other questions. And finally, ending up with this whole concept, this practical concept of why we naturally feel to take short steps on slippery surfaces. Thank you for watching.